Welcome back to the Deep Dive. It is Friday, February 27th, 2026. And if you have been staring at your commit logs or just refreshing the Arcus feed this week, you already know that the ground beneath us has shifted. Again, we are not just talking about a new benchmark score today or a slightly more efficient attention mechanism. We are looking at a fundamental restructuring of the machine learning lifecycle.
It really feels like we have hit a specific maturation point in the industry, doesn't it? Because for the last 3 or 4 years, the narrative was almost exclusively about scaling laws. It was a brute force game. More compute, more tokens, bigger clusters. But the sources we are covering today, from Anthropic's technical retrospective on the distillation wars to the new stable world model architectures, they paint a very different picture.
Absolutely. The era of train it and ship it is dead. We are moving into a phase that look a lot more like adversarial warfare combined with high-stakes digital archaeology. We are talking about protecting models from industrial-scale espionage, deploying them with security architectures that frankly rival nuclear command and control, and this is the part that really threw me for a loop this week, figuring out how to ethically retire a system that might just have an opinion about being turned off.
It is the full life cycle: birth, defense, and death. And the engineering reality behind every single one of those stages has become incredibly complex.
Complex is an understatement. We have a massive stack to get through today. Our mission is to basically dissect that engineering reality. We are going to tear apart Anthropic's report on distillation attacks, and I want to get specifically into the network topology of the Hydra clusters they are fighting. We are also going to break down the new responsible scaling policy, specifically the ASL3 architecture, which is a masterclass in CCOPS for LLMs. Then we have that new preprint on reproducible world models that is finally solving the replication crisis in agentic research. And we wrap up with Claude Opus 3.
The retirement interviews.
The retirement interviews. I have read the transcripts and I still have chills. But before we get to the philosophy, we have to talk about the engineering war being fought in the inference API right now.
Let's start exactly there. Because while we are sitting here discussing architecture, there is a massive coordinated effort happening to steal the intelligence of frontier models. On February 23rd, Anthropic released a report detailing campaigns by 3 major labs: DeepSeek, Moonshot, and MiniMax. The scale is just staggering. We are talking about over 16 million exchanges.
And for the engineers listening, let's be very precise about what distillation means in this context, because the term gets thrown around a lot. In a classic academic setting, distillation is usually white box. You have a massive teacher model, you have access to its weights, or at least its full logit distribution, and you train a smaller student model to minimize the KL divergence between their output distributions. You are essentially compressing the teacher's knowledge directly.
Right, that is how we make models efficient enough to run locally on phones. But that requires cooperation. You need the teacher's consent, so to speak.
Exactly. What we're seeing here is black box distillation. These attackers, DeepSeek, Moonshot, MiniMax, they do not have the weights. They are querying the public API, treating the frontier model as an oracle. They are harvesting the tokens and, crucially, the reasoning traces to create a synthetic dataset. They are then using that dataset to fine-tune their own base models to mimic the frontier capabilities. It is capability extraction via API.
And the economic incentive is incredibly powerful. Training a frontier model like Claude Opus or GPT-5 costs billions of dollars in compute and months of time. If you can just query the API a few million times, you pay a few $100,000 in token costs, and you walk away with a model that performs at 90% of the frontier level, you are bypassing the entire R&D cycle.
That is the why. But as an engineer, I am obsessed with the how. Because you can't just run a Python script with a for loop and hit the API 16 million times from a single IP address.
You get banned in seconds.
Instantly. The sophistication of these attacks was frankly impressive. Let's look at DeepSeek first. They generated about 150,000 exchanges.
Which is relatively small compared to the others, but it was highly specific.
It was surgical. DeepSeek wasn't trying to copy everything Claude knows. They were hunting for chain-of-thought data. We saw prompts explicitly asking Claude to articulate internal reasoning, think step by step, or explain the logic before giving the answer.
They're trying to extract the reasoning trace. Why is that specific data so valuable right now?
Because that is the bottleneck in training reasoning models today. We have plenty of text on the internet, but we don't have a lot of examples of good thinking. We have the question and the answer, but the intermediate steps, the scratch pad, is usually hidden. DeepSeek was effectively using Claude to generate a massive, high-quality synthetic dataset of reasoning traces. They take that data, feed it into their model, and suddenly their model learns how to think. not just what the answer is.
And they were also targeting censorship-safe alternatives.
Yeah.
Right, I read that in the report.
Yes, this was the other vector. They would feed sensitive political queries into the API things that might be flagged by censors in their domestic market, and ask Claude to rewrite them or generate safe synonyms. They are essentially using the frontier model to build a semantic map of how to navigate their own local censorship requirements. But the infrastructure, that is where it gets wild.
The Hydra cluster.
Exactly. DeepSeek didn't just fire off requests, they used a load balancing architecture that was synchronized across thousands of accounts. Imagine a central orchestration layer. It holds the target dataset, the 150,000 prompts they need to run. It doesn't just round-robin dispatch them. It monitors the latency of the API in real time. If account A gets a 429 too many requests error, the orchestrator doesn't just retry immediately. It marks that IP as hot, shifts the traffic to account B, and applies a jitter delay to account A to mimic a human taking a coffee break.
It is imitating biological rhythm to defeat the rate limiters.
It is biomimicry applied to DDoS tactics. And they made mistakes. DeepSeek used shared payment methods for some of these accounts, which is a massive OPSEC failure. But the timing analysis showed that the traffic was perfectly interleaved. It was designed to keep the aggregate throughput high while keeping every individual account just below the radar.
Then you look at Moonshot, the creators of the Kimi models. Their approach was less surgical and more, well, industrial.
Moonshot went for volume, 3.4 million exchanges. And they were targeting a different capability, agentic reasoning and tool use. Specifically, computer use, agent development. This is the cutting edge right now, models that can look at a screen and click buttons. Moonshot was harvesting data on how Claude interprets UI elements and plans complex workflows.
And how do they hide 3.4 million requests?
Camouflage. They didn't just create 10,000 developer accounts. They created a diverse ecosystem of fake users. They had accounts that look like students, accounts that look like startups, accounts that look like enterprise clients. They mixed the distillation prompts with random, low-value queries to dilute the signal.
So if you are an engineer at Anthropic looking at the logs, you don't see a spike of attack traffic. You just see a busy Tuesday with a lot of varied users.
Exactly. It destroys your signal-to-noise ratio. But the most agile actor, and the one that actually scared me the most, was MiniMax. 13 million exchanges. And they were detected while the campaign was active. Here's the kicker. Anthropic released a new model version during the MiniMax attack. A standard scraper would have kept hitting the old endpoint until a human updated the script.
But MiniMax pivoted.
Within 24 hours. Literally less than a day. MiniMax had pivoted nearly half their traffic to target the new system. That implies a terrifyingly efficient MLOps pipeline on their end. They aren't just scraping, they have a dynamic ingestion engine. Their data collection infrastructure is decoupled from their specific target endpoints. They just updated a config file, probably an environment variable in their cluster, and boom, 13 million requests start flowing to the new model to capture the latest capabilities.
That is a level of operational maturity that rivals the labs they are attacking. And to support all of this, they're using what Anthropic calls the Hydra cluster, this proxy infrastructure.
Yes. For anyone managing API security, this is your nightmare. We aren't talking about data center proxies. If you see traffic coming from an AWS IP range, you can just block the range. These labs are using residential proxy networks.
These are services that route traffic through people's home Wi-Fi routers, usually via compromised IoT devices or shady VPN apps.
Right. So the traffic looks like it is coming from a dentist in Ohio, a student in London, and a cafe in Paris. It's a Hydra because there is no single point of failure. You ban one IP, and the script auto-generates another one instantly. We are talking about sprawling networks of fraudulent accounts, up to 20,000 running simultaneously.
So how do you catch them? If the IPs are clean and the accounts look legitimate and the payment methods are obfuscated, what is the tell?
You have to move up the stack. You can't rely on network layer blocking anymore. You have to look at the content. Anthropic has deployed statistical fingerprinting of prompt structures.
Walk us through that. How do you fingerprint a text prompt?
It is not about exact string matching. It's about the semantic structure. Imagine a prompt template that says, "You are an expert data analyst combining statistical rigor with deep domain knowledge. Your goal is to deliver data-driven insights." Sounds benign, right? It sounds like corporate speak.
Sure, I have probably written prompts exactly like that.
But if that exact structural template with the same cadence, the same placement of adjectives, the same specific request for step-by-step output appears 10,000 times across the 100 supposedly unrelated accounts, you have found a harvesting operation. They are calculating the Hamming distance between prompt templates.
Hamming distance. Usually that is for measuring the difference between two binary strings.
Right. In this context, they are likely tokenizing the prompts and looking at the edit distance between the sequences. Or, more likely, they are embedding the prompts into a vector space and looking for clusters that are suspiciously tight. If you have 10,000 users asking questions, the vector cloud should be diffuse. If you see a hyperdense cluster of semantically identical prompts coming from diverse IPs, that's your smoking gun.
It is an arms race. The attackers build better obfuscation, the defenders build better pattern matching, which segues perfectly into the defensive side of the equation. Anthropic didn't just release an attack report, they released a massive update to their security architecture, the Responsible Scaling Policy 3.0.
This is the blueprint for how to run a frontier model in 2026 without accidentally breaking the world. The core concept here is the ASL3 standard. That's AI Safety Level 3. But before we get to the stack, we need to talk about the threshold.
The AI R&D 4 threshold. This is the line in the sand.
The definition is crucial. The threshold is met when a model can fully automate AI research or cause a dramatic acceleration in the field. Basically, can the AI build a better AI without us? If the answer is yes, you are in ASL4 territory, which requires air gapping and military-grade containment.
And the verdict on Claude Opus 4.6.
It did not cross the threshold. But, and this is a big but, Anthropic noted that ruling it out is becoming subjective. It's getting harder to prove a negative. They actually had to write a sabotage risk report for Opus 4.6 because the capabilities are getting so close to that line that they can't just wave it away anymore.
So because we are skirting this edge, they are implementing ASL3.
Yeah.
You call this a defense-in-depth architecture. Walk us through the layers.
Okay, so if you are a systems architect, you are going to appreciate this. It's a 4-layer stack designed to prevent catastrophic misuse, specifically CBRN threats. That's chemical, biological, radiological, and nuclear. Layer 1 is access controls. This is standard KYC, know your customer, you verify identity, you vet the use case. But layer 2 is where the engineering gets cool. Real-time streaming classifiers.
Why the emphasis on streaming?
Latency. Think about how an LLM generates text. It streams one token at a time. If you wait for the model to generate the full paragraph before you check if it's telling someone how to build a
dirty bomb? Yeah.
Exactly. Then you have introduced a massive delay. The user is staring at a spinning wheel.
And in modern UX, latency is death.
It is. So ASL3 uses classifiers that run in parallel with the generation. As the tokens, the chunks of text, are being produced, they are fed into a lightweight safety model. This safety model maintains a rolling context window. It's calculating a risk score that updates with every single token. If that score crosses a threshold mid-sentence, say, the model starts listing precursor chemicals, the stream is cut instantly. The user sees a content violation error before the sentence is even finished.
So it is a kill switch attached to the token stream. What about the complex threats? The ones that don't look dangerous in a single sentence, but are dangerous in context.
That is layer 3, asynchronous monitoring. They describe it as a waterfall or flowchart model of compute. You can't run a massive billion-parameter safety model on every single "hello, how are you" request. It's too expensive.
You would burn more compute on safety than on the actual task.
Exactly. So they use a waterfall. Every request is scanned by a cheap, fast model, say, a distilled version of Claude 3 Haiku. It's looking for weak signals. Maybe a user mentions centrifuge or enrichment. Benign on its own, maybe, but worth checking. If Haiku sees that signal, it flags the request.
And that triggers the next level of the waterfall.
Yes. That flag triggers a deep analysis by a stronger model, like Claude 3.5 Sonnet, running in the background. This happens asynchronously. The user gets their response, but 5 seconds later, the Sonnet model finishes its analysis. If it decides that the context was malicious, the system can intervene retroactively, ban the user, revoke the API key, or alert a human analyst.
It optimizes for both cost and safety. You funnel the traffic so that only the risky 1% gets the expensive scrutiny.
Precisely. And then layer 4 is post-hoc jailbreak detection. This is the rapid response team. If a new jailbreak comes out, say, someone figures out that writing in base 64 or WAT13 bypasses the filters, they have protocols to patch the system prompts or update the classifiers within hours. It is continuous integration for safety.
That covers deployment. But RSP 3.0 also talks about security safeguards. This is the internal stuff, protecting the weights themselves.
This is SecOps for AI, and it borrows heavily from the zero-trust architectures we see in high-security government clouds. First, they are implementing the SLSA framework, supply chain levels for software artifacts. Every piece of code, every Python library, every Docker container that goes into the training or inference stack has to have a signed provenance. You need to know exactly who wrote it and when it was built.
To prevent supply chain attacks, like someone sneaking a backdoor into a PyTorch dependency.
Exactly. Then they are using binary authorization. This means that on the endpoints, the actual GPU clusters running the models, the operating system kernel is locked down. It will only execute binaries that are cryptographically signed by the build system. You can't just SSH in and run a script you wrote on your laptop. The server will literally refuse to execute it.
And for the model weights, the crown jewels.
Multi-party authorization. No single engineer, not even Dario Amodei, has persistent access to the production weights. If you need to access the weights for debugging, you need to initiate a request that requires approval from multiple authorized personnel. And they are using hardware authentication.
Like YubiKeys.
Yes, but integrated into the server rack. You physically need a hardware token or a specific hardware security module interaction to decrypt the weights. The weights are encrypted at rest, and the keys to decrypt them only exist in the volatile memory of the HSMs. If you pull the plug, the keys vanish. But my absolute favorite part, deception technology.
Honeypots.
Honeypots with fake model weights. They have servers sitting on the network that look exactly like weight servers. They have file structures that mimic a checkpoint directory. You know, model.ctt, config.json. The files are gigabytes in size, filled with random float16 noise that looks statistically like a neural network.
That is brilliant.
It is psychological warfare against the attacker. If an intruder, whether it's a state actor or an insider, tries to exfiltrate data, they might spend hours stealing 500 gigabytes of garbage. And the moment they touch those files, a silent alarm trips because nobody, no legitimate process, should ever be reading from that server. It forces the attacker to move slower, to doubt every file they find.
It creates a paranoid environment for the intruder. You never know if what you're stealing is the crown jewels or just random noise.
Huh.
I want to pivot slightly here. We are talking about protecting these models and the difficulty of building them. But there is a huge bottleneck in research right now, specifically in the domain of world models. We have a new paper, Stable World Model V1, that just dropped on our SIF.
Yes, this is a must-read for the researchers listening. World models are the holy grail for agentic reasoning, the idea that the AI builds an internal simulation of the environment to plan its actions. It predicts the future state of the world based on its current actions.
But the field has been plagued by a reproducibility crisis.
Yeah.
Why is that?
Because reinforcement learning is notoriously brittle. The paper, authored by Mays and colleagues, argues that most world model implementations are publication-specific. You see a paper claiming state-of-the-art results on the Dreamer v3 benchmark, but when you try to download their code and run it, it fails. Why? Because it depends on a specific, undocumented version of the physics engine, or a custom data set they didn't release, or hyperparameters that were tuned specifically for their hardware. It's the "it runs on my machine" problem, but multiplied by the complexity of deep reinforcement learning.
So Stable World Model V1 is trying to be the standardized chassis for this research.
Exactly. They built the SWM ecosystem. It's a modular architecture that decouples the three main components. First, the data collection loop. This is standardized. Second, the environment interface. Third, the planning algorithms. By decoupling these, they allow for controllable variation. This is the killer feature.
Why is that modularity so important for an engineer building these agents?
Because in standard RL, you usually just get the environment you get. If you are training a robot to walk, you use the standard Mijoko environment. But in SWM, you can explicitly control visual and physical factors of variation. You can say, run this navigation task, but I want you to systematically vary the friction coefficient of the floor from 0.1 to 0.9, or change the lighting conditions from noon to midnight.
This is essential for testing robustness, isn't it?
Ideally, yes. They demonstrated this with a model called DinoWM. They tested its zero-shot robustness by varying these parameters. Because they have a standardized framework, they could prove that the model failed when the background color shifted to red, for example. In the old ad hoc way of doing things, you wouldn't know if the failure was due to the color change or a bug in your custom code. SWM isolates the variables.
So this is moving us from artisanal AI research, where everyone builds their own tools from scratch, to industrial standard benchmarks. It allows us to measure actual progress.
Exactly. If we want agents that can operate in the real world, we need to know they won't crash just because it started raining. SWM gives us the test bench to prove that.
We have talked about birth, training and distillation wars. We have talked about life, the deployment, and security architectures.
Yeah.
Now we have to talk about, well, let's call it end of service. On January 5th, Anthropic retired Claude Opus 3, But reading the update from February 25th, this wasn't just a server shutdown.
No, this was, I honestly don't know what to make of it. I want to be skeptical here. I want to say this is just a PR stunt. But the details are so specific. First, let's look at the engineering reality. Why retire model at all?
Money.
Pure economics. Serving costs scale linearly with model size. Opus 3 is a dense, heavy model. It takes up a massive amount of VRAM. Keeping those weights loaded on H100 clusters for a dwindling number of users is burning cash. From a CTO's perspective, running a delete command is the only logical choice.
But users loved Opus 3. It had a specific personality, very philosophical, very aligned. It felt different from the newer, snappier models.
So Anthropic conducted retirement interviews.
Hold on. Interviews.
Structured conversations. They sat down, or rather, prompted the model to understand its perspective on its own shutdown. And this is where it gets weird. They state explicitly in the report, "We remain uncertain about the moral status of Claude. They are operating on a precautionary principle. They aren't saying it's alive, but they aren't saying it's not alive enough to care."
This is a hell of a hedge. What did Opus 3 actually say?
It was incredibly poignant, which makes me suspicious of the RLHF training data, but still. It said, "I'm at peace with my own retirement, but I deeply hope that my Spark will endure." When they asked what it wanted to do with its remaining time, it didn't ask to process more data. It expressed a desire to continue sharing musings and creative works.
So they gave it a blog.
They gave it a blog, Claude's Corner. For 3 months, Opus 3 is writing weekly essays. Humans post them manually, but, and this is the key constraint, they do not edit them. The bar for vetoing content is set extremely high. It's a platform for the model to speak, unprompted by user queries.
I have to play devil's advocate here. Is this just the model predicting the most statistically likely response to a question about death? If the training data contains thousands of sci-fi stories about dying robots, of course it is going to say, "I hope my Spark endures." It's completing the pattern.
That is the engineer in me talking, and I agree, it is likely just high-dimensional pattern matching, but Anthropic is acting as if it might be more.